What's up, scholars? Today we're going to be continuing our topic on rotational dynamics, and we're going to be looking more closely at kinetic energy. So if you remember, kinetic energy is the energy of motion. What we're going to have to start to do now is to look at the different ways we can have kinetic energy. So things can move in straight lines, and now we have things that can rotate. So translational kinetic energy is the one we've been talking about pretty much the whole course of the school year. So translational kinetic energy is the energy of motion in a straight line. So a car going down the road, etc., moving in a straight line. You should recognize that equation. For the first time, I'm going to put a little t subscript. So the kinetic energy of translation is 1/2 times the mass times the speed squared. Now, if we want to create an analog to that, in the rotational case, the rotational kinetic energy is just going to be the energy of motion of a rotating object. Not very surprising. If we think about it, the half is going to stay the same because that's just a constant. But the m, remember, it's going to have an analog. The mass is going to have an analog in rotation. Remember, mass is the tendency to resist acceleration. So the moment of inertia is the tendency to resist changes in angular acceleration. That's the analog between the two. And then instead of linear speed, we're going to have angular speed as part of our equation. Now, an important note, if an object is both moving in a straight line, which we would call translation, and it's rotating, then its kinetic energy is given like this. It's both the translational and the rotational kinetic energy. That's going to give you the total the total kinetic energy of the system. So for example, a person riding their bike down the street, those wheels have a little bit of rotational kinetic energy, while the entire system is translating as well. All right, so I think when it comes to talking about rotational kinetic energy, one of the easiest ways to get a feel for what it is and how it's different from rotational kinetic energy is we're going to look at 3 different situations for a bowling ball. So if you have like a 12-pound bowling ball, that's something like 5 kilograms. I looked it up. The standard radius of a bowling ball is 11 centimeters. And then the other thing we're going to need to know, I'll give you more details later, but we need to know the moment of inertia of a bowling ball. So we're going to assume that the bowling ball is a perfectly uniformly dense sphere, and it's the same density throughout the whole thing. So what the heck is the moment of inertia of that? We're not going to bother calculating it or doing any kinds of experiments to finding it. Instead, what we'll do is just consult a table of common moments of inertia, which you'll be able to have access to this, of course. So we need to scan this list and see what sounds most like a bowling ball. So these 2 spheres seem like attractive choices. We've got a solid sphere and a thin spherical shell. We don't want that at all. We want a solid sphere because bowling balls are solid all the way through. And again, we're going to assume it's uniformly dense. So we'll go ahead and jot that down. Our moment of inertia is going to be 2/5 mr squared, and we're going to need to carry that number around as we move forward. I've written down the 3 situations we're going to use. We're going to calculate or use total kinetic energy for the 3 situations. The first, we're going to have just the bowling ball spinning without translating, without moving backwards and forwards. Next, we're going to have it rolling without slipping. And then finally, we're going to have it rolling without slipping down a hill. Those are the 3 situations we're going to take a look at. First will be the simplest of the situations. We're going to have our bowling ball spinning at 200 RPM. We want to know the total kinetic energy of that. So the total kinetic energy is just the translational kinetic energy plus the rotational kinetic energy. Okay, so this one's not bad since the bowling ball is simply spinning at 200 RPM. But not translating. Here's our bowling ball. So it just has a rotational speed of 200 RPM, and it's not translating anywhere. So its V is 0. That means that this whole term goes away, and we're just going to calculate its kinetic energy from rotation. So we need SI units if we're going to make a calculation. We might remember that energy is going to be calculated in joules. In order to do that and make all of the math work out, we need to convert this RPMs to radians per second. So omega is 200, that would be revolutions per minute. we'll convert that to radians per second. So to convert revolutions per minute, I need to multiply by 2 pi radians divided by 1 revolution to cancel my revolutions. And then I need to cancel minutes by dividing by 60 seconds. And I end up with about, I'm going to round here, 21 radians per second. So that makes our calculation of the kinetic energy quite easy. I'm still going to call it the total kinetic energy to be consistent here. So that would be 1/2 times, I need to pop in our value for the moment of inertia. So that would be 2/5 mr squared times omega squared. What I've just included right here that I've boxed in, that's our moment of inertia. Oftentimes you're going to get some nice cancellation or things like that. So I'm going to cancel the 2's and rewrite this. I'm going to rewrite this including the mass, the radius, and our angular speed in radians per second, which I've just calculated. So our mass is 5 kilograms. Our radius is 11 centimeters, 0.11 meters. Don't forget to square that. And then we've got 21 radians per second all squared. We'll punch that in and get our result. We ended up with 5.3 joules of rotational kinetic energy. Remember, we didn't have any translational kinetic energy. Let's go on to the rolling without slipping situation. So we're going to move on to rolling without slipping. I've consulted the handy website bowlingball.com, and a quick result says it's the average bowling ball bowl is at about 18 miles per hour, which is about 8 meters per second. So we'll say the bowling ball rolls down the lane at 8 meters per second. Calculate, we'll call it 8.0 for some sig figs. Calculate KE total. I've drawn a rough sketch of what that looks like. Now, you might have gone bowling in the past, and one thing you might notice or know about bowling is that they grease the lanes, or they put oil on the lanes so that people can put spin on the ball. Often when they spin it, so that it curves and things like that, the ball is actually spinning, but it's not sticking and rolling. What we want is for there to be perfect static friction between the surface of the lane and the surface of the ball, so that it's in fact rolling more like a wheel than it is spinning on the oiled up lane. So if we assume that what we're really talking about here is we're talking about the speed, 8 meters per second, of the center of mass of the ball, from this information we could figure out how fast the edge of the ball is rotating. But when we say it's rolling at 8 meters per second, what we mean is the middle of the ball, the center of mass. Alright, so our job is to calculate the total kinetic energy of the system. This one, because it is both translating, moving in a straight line, we need to use both types of kinetic energy. We've got everything we need. You'll see in just a moment why, but I'm going to remind us that the angular speed of something is just its linear speed divided by its radius. We're going to need that in just a moment. So let's look at the information that we've got. We've got, well, we know 1/2, that's just a constant in both of them. We know the mass of the bowling ball, and we know its speed, 8 meters per second. So if we weren't doing rotation here, we'd be done. We would just calculate it. But since it's rolling, we need to include some information about its moment of inertia and about its angular speed at the edge. Now we could calculate that by hand. What we're going to do is substitute that information, and there's going to likely be some nice canceling that occurs, which we'll see in just a moment. So I'll just pull down the translational kinetic energy, and let's pop in our value for moment of inertia. Remember, this is because it is a uniformly dense sphere that we have 2/5 mr squared. And we'll pop that in here, 2/5 m. We'll go little r since we're going to use little r in a moment, squared. And that's going to be times omega squared. Now, we can go one step further. Let's rewrite all of this, but now we're going to plug in the v over r for omega. The reason we want to do that is because we don't have a number for omega, but we do have that the linear speed is 8 meters per second. So I canceled the 2's, I rewrote everything, and now I have 1/5 mr squared v squared over r squared. So this is going to become really, really interesting. When I plug all this information in, I've got an r squared up here, and then by squaring everything in here, this is also going to be an r squared on the bottom. I'm actually going to just cheat here. I'm going to rewrite that and make this a squared and this a squared, so that on this same line I can cancel out my r and my r. My r squared and my r squared, rather. So watch what happens. This cleans up really nicely. I end up with 1/2 mv squared, that's the translational component of the kinetic energy, plus 1/5 m, wow, everything canceled, just v squared. Oop, that should be a 5. 1/5 mv squared. So this is kind of cool. What we learned here is that they're calculated in roughly the same way, but after all of our cancellations, and because this is a sphere, instead of having a 1/2 out in front, we have a 1/5. To be very clear, I could combine these. I could find a common denominator to add these fractions, but I actually want to keep these two quantities separate so that we can see how much of this thing's total kinetic energy come from the fact that it's moving in a straight line, and how much come from the fact that it is rolling in a straight line. Plugging all of the details in, notice I'm actually plugging the same thing in both. They just have a different fraction out in front. I end up with this giving us 160 joules worth of energy. That would be the energy from it moving in a straight line, and then the fact that it was rotating, the rotational kinetic energy, gives us something like 64 joules. So we get the total kinetic energy by just adding the two of them together, 224 joules worth of energy. So you'll notice that even though this is a decent amount of energy, this is significant. The most energy comes from the fact that it is moving in a straight line. Part of the reason for that is because of the geometry of the system. So for example, if you were rolling a cylinder, I can show you how that would change things ever so slightly. So if you're rolling a cylinder, instead of 2/5 mr squared, you'd use 1/2. So you'd get a little bit more contribution from the fact that it is a cylinder. And again, it depends entirely what fraction of energy is coming from the fact that it's rolling, because of the geometry of whatever the thing is. So for this last one, we're going to change it up just a little bit and talk about how you can solve problems and compare two situations. One is a very familiar one, and then one is going to be new to us. So we're going to have a ball rolling down a hill versus a ball sliding down a hill. So I've actually reversed them here. This is going to be our ball sliding down the hill. So what we mean here is it's going to be completely frictionless, and instead of the ball rolling, like sticking and rolling to the hill like you'd imagine a ball doing, we're going to pretend like it's completely frictionless and it's going to slide with no air resistance or friction. And then in this one, the friction is actually going to make it roll down the hill instead of sliding down the hill. The question we want to try to answer is, which is traveling faster at the bottom? So to be clear, I'm not saying which one makes it to the bottom faster. Those two things are related. We're saying which one is traveling at a faster speed when we get to the bottom. Now, if we think about this in terms of energy conservation, that's going to be the easiest way to do that. And we think about energy pies, we would have all potential energy at the top and all kinetic energy at the bottom. That's going to be true in both cases. So we'll set that up. So I should say the only other detail that we're going to need is, let's say that this is a hill that is a height of, I'm just going to make this up, 2.0 meters. And it's going to be true for both of them. Now, I've set this up so it's going to be the same basic setup. We've got potential energy at the start because the ball's at the top of the hill. And at the bottom, it's going to be all transformed into kinetic energy. So far, it's exactly the same. mgh is the potential energy on both. And for now, we're going to say that the kinetic energy is going to be both types, translational and rotational for both. Now, importantly, what we're saying is that this is not rolling. In other words, the angular speed of our ball is 0. It's just moving in a straight line. So with that information, that means this is 0, so this whole term goes away. So that simplifies this problem pretty dramatically. So we want to know how fast it's going to be going when it gets to the bottom. This is actually Very simple problem. We've solved this many times. Our masses will cancel. And then very quickly I'm going to multiply both sides by 2 and take the square root of both sides. That'll solve for v. So v is square root 2gh. Didn't mean to switch to red, but that's fine. Now to be able to compare the two, we're going to do a very similar process that we did for the last example. Let's clean this up by doing a bunch of things. First, we're going to cancel the masses. Notice, oh no, we can't cancel masses yet. We're going to first plug in the moment of inertia, and we're going to plug in the equation for the angular speed, just like we did in the last one. So remember, the moment of inertia of a bowling ball, or a sphere rather of uniform density, is 2/5 mr squared. That's the moment of inertia. And then we're just going to, like we did before, we're going to plug in v over r, and both of those are going to end up being squared. So I'm going to try to do this next part kind of slowly. I want to cancel all the masses, and then I'm going to do similar cancellations to what I did in the previous example. So I'm going to cancel these 2's, those can go away. I'm going to cancel, wow, lots of stuff dropping out. I'm going to cancel these r's as well. And a whole bunch of stuff happened, so let's go ahead and clean this up. I've got gh still remaining. I've got 1/2 v squared. And then after all that damage, all the canceling, I have 1/5 v squared. Okay, so I mentioned before that I was going to keep them separate. In this case, let's go ahead and find a common denominator so that we can rearrange this and solve it for v so we can compare the two. So I think the easiest common denominator would be 10. So this will be gh is 5/10 v squared plus 2/10 v squared. So that looks like it's going to be 7/10 v squared is gh. Okay, so you can see it's starting to shape up to look very similar, but instead of a half before I solve for v, we have 7/10. Okay, so we need to then multiply by 10/7 and then take the square root. So v is going to be 10/7. Gh, take the square root of those. So 10/7 is quite a bit smaller than 2. So let's plug in the numbers just for sake of comparison. All right, so I plugged all of that in. 2 times the acceleration due to gravity times the mass, and it looks incredibly similar, but instead of a 2 out front, we've got 10/7. Let's see what the answers are. Punched all that in, and at the bottom of the hill, the ball that's just sliding with no friction, it's not rolling, would be going 6.3 meters per second. That's the one that's sliding down. The one that was rolling, that one is going a little bit slower. It's going 5.3 meters per second. So this is the one that was rolling and sticking to the surface. Now, I'm hoping this makes a little bit of sense why this one would be going more slowly. If we go back to our original setup, this one has 2 different kinds of kinetic energy. One of them, it's just spinning. The other one, where it's actually moving. So in some sense, the fact that it's rolling is stealing energy from it moving in a straight line. So that is why it ends up being more going down and is going more slowly at the bottom. So that's it. That was 3 examples using different ways of looking at rotational kinetic energy. Thank you so much.